Okay, welcome everyone to another episode of the BJ's Physics Classroom. This section of the Physics Classroom is going to deal with practicals. We want to, do some practicals. And the practical for today, this section is going to be based on wave motion and sound. Before we left school for home, we had dealt with wave motion. We were yet to do the practical aspect of it when the COVID-19 came and we had to go home. Just a reminder, I have my nose mask with me, so make sure that we stay safe. It is very important. If you are in public, make sure you put on your nose mask, sanitize your hands, and the rest. But here I'm alone, so I'll put the nose mask away. Good. So we are going to describe a simple experiment to determine the velocity of sound in air using resonance tube and several tuning forks. So what I do is that I have some few set of tuning forks here, tuning forks of different frequencies. I need a resonance tube, so I had to improvise one. So what I did was that I obtained an open pipe. This is an open pipe, both ends opened. Before I can make this on a resonance tube, one of the ends must be closed. So what I do is that I pick a transparent glass. Then I fix this calibrated open pipe in the glass. Then what I do is that I pour water into the tube and make sure that it is up to the level that I want to use it. So now, this is my resonance tube. To help me hold this, I bring in a retort stand so that when I tighten the retort stand, I can get a full set of resonance tube. So this is my resonance tube. So I have a resonance tube and I have a set of tuning forks that I'm going to use for this experiment. So let me write the topic on the board so that you can have it. So the practical or the topic is determination of velocity of sound in air using resonance tube. Good. So to do this, we need a table. After I have obtained the values, I need to put the tables in the values in the table so that I can plot graph. So what I do is that in the table, we are going to need frequency. That is the frequency of the tuning fork. So F is to hertz, that is the unit for frequency. Then L, that is the length of the pipe, the length of the resonance tube, L stroke centimeters. And then frequency inverse, stroke hertz inverse. Later, when I'm done with the description of the experiment, I will take you through the basic theory behind the reason why I'm picking these values, I'm picking these quantities, and I'm finding the inverse of the frequency. When I take you through the theory, you get to see the reason why I did that. Good. So I'll pick the tuning forks one by one, then I'll write their frequencies. So the frequency of this tuning fork, is 512 Hertz. So this is 512. The frequency of this tuning fork is 480. The frequency of this tuning fork is 426. And the frequency of this tuning fork is 320. 320. I need at least 5 of them, and I have 5. And this is 256 hertz. 256 hertz. Good. So this is my table. So once I have put the frequencies on the table, I will go through the experiment. Good. So let me bring on my resonance tube. Okay. So let's begin with the actual practical. How do we do this? We know that the frequency of a tuning fork is inversely proportional to the length when resonance occurs. So what I'm going to do is that I'll pick the tuning forks one after the other. I'll sound the tuning fork and place it on top of the resonance tube, so that as I vary the length of the resonance tube, I expect resonance to occur. Remember, at resonance, a loud sound will be heard. The moment I hear the sound, then I will stop and measure the length of the pipe. So the tuning fork I have picked is 512 hertz. So I'll sound that tuning fork like this. You see? Loud sound. Let me do it again so that you hear. So that is when resonance is occurring. Then I will do this. Then I will tighten this one so that I can measure the length. Now the length of the pipe from the open end to where the level of the water is. This is giving me 17. This is 16.6 centimeters. So the length that corresponds to the frequency 512 is 16.6 centimeters. Remember that the least count of a ruler is 1 decimal place. So this one is in 1 decimal place. Thank you. So I'm done with that tuning fork. I'll put it aside. Then I'll pick the next tuning fork. The next tuning fork is 480 hertz. 480 hertz. So I'll sound that tuning fork again. Let me unscrew this and make it loose. I'll sound that tuning fork again. So this is where resonance is occurring. Then I will determine the length. So the length is 17.2 centimeters. So that will give me 17.2 centimeters. 17.2 centimeters. I'll put that tuning fork to your side. Then I'll pick another one. So you continue to do this until all the lengths at which resonance is occurring are obtained. Good. So the next one, which is 426. Sorry, let me unscrew this one. 426. So resonance has occurred. So what I do is that I will then screw this. Then I will determine the length. So the length is 19.2 centimeters. 19.2 centimeters. 19.2 centimeters. 19.2 centimeters. Sorry, the stopwatch was disturbing me, so I had to put it off. Good. So I will continue with the next. This one is 320. So I'll pick the 320. Now, remember that as the frequency decreases, it affects the note, the frequency of the note. Sorry, as the frequency decrease, the sound, the intensity of the sound decrease. So please be careful with it. At this point, if you don't listen carefully, you will not hear the sound. So listen carefully, attentively. Good. So this is the point where resonance occurs. Then the length is 26.2. No, it's 26.2 centimeters. So that will give me 26.2 centimeters. 26.2 centimeters. I'm left with one last tuning fork. Good. So I'll sound the tuning fork. Now the frequency of this one is 256. Listen to this one carefully, else you will not hear it. This is 256 hertz. So I'll sound it. Good. Loud sound. Let me do it again so that you hear. At this point, it's a little bit difficult, so let me do it again. I hope you can hear resonance occurring. Good. So what I will do is that I will tighten this one. Then I'll look at the length. Now the length at this point is 22.4 centimeters. The length at this point is 22.4 centimeters. 4 centimeters. Good. So now I'm done with the practical. I have determined the lengths that correspond to the frequencies. The length that correspond to the frequencies. Now, as you can see on the board, as the length is increasing, the frequency is decreasing because the frequency of an open pipe, the frequency of sound is inversely proportional to the length of the resonance tube or the length of the pipe. Good. So once we have done this, what we do is that we find the inverse of the frequencies. And then we plot a graph of 1/f against the length. Why are we doing all that? Let me take you through the theory behind this one small. So for the purpose of the distance, let me clean this one. Good. For a tuning fork that is sounding is fundamental. Remember, all the tuning forks sounded their fundamental frequencies. What is the fundamental frequencies? The first frequency of a note produced in a pipe, whether closed pipe or open pipe. The frequency of the first note produced, that is what we call the frequency, the fundamental. Now the fundamental frequency F is given by V/4 into bracket L plus C, where C is the end correction. What is end correction? That is the distance between the open end of the pipe and the antode. The distance between the open end of the pipe and the antode. As resonance occurs, the fundamental is given by this. Let this be the pipe. You know, I sound the tuning fork and I place it on top of this one like this. This is the tuning fork. So the tuning fork vibrates to generate a stationary wave within this pipe. So when the pipe is sounding is fundamental, the wave inside the pipe is like this. The wave inside the pipe is like this. Okay. The wave inside the pipe is like this. Then, so the length of the pipe is L. The wavelength. How many wavelengths are here? 1/4 lambda. There are 1/4 wavelengths here. Good. But look at this critically. Look at the wavelength. The wavelength starts from here to here. But you can see that the length of the pipe starts from here. What that means, there's an error. And that error is the distance from here to here. So that error that we try to take care of is what we refer to as the end correction. The distance between the open end of the pipe and the antinode. This point is the antinode of the wave. So we call that C. We call that C. Now look at this. From that diagram, we can see that L plus C is equal to 1 over 4 lambda. 1/4 of the wavelength. That is L plus C. L plus C is equal to 1/4 of the wavelength. So we make lambda the subject. We get lambda is equal to 4 into bracket L plus C. Okay. Then we pick this. But velocity of sound, V is equal to lambda F, where F is the frequency. So we make F the subject. F is equal to V over lambda. Good. So for that matter, we put lambda equals 4L plus C at this, in place of this one. Then we get F is equal to V over 4L into bracket, 4 into bracket L plus C. That's what I've written here. Alright? So this is the fundamental frequency of a closed pipe. In other words, resonance tube. Good. So let me clean this. I hope I've already taken you through this already, so there's no need. Okay. Then we manipulate this equation and try and make 1 over F the subject of this equation. So what I'm going to do is that let me rearrange this equation and make 1 over F the subject. So if I do cross multiplication and then I divide 2, I'm going to get L plus 4L plus 4C is equal to V over F, like this. Then I'll divide the equation by V. So I'm going to get 4L over V plus 4C over V is equal to 1 over F. Good. I've made 1 over F the subject. So swapping the positions of this, I'm going to get 1 over F is equal to 4L over V plus 4C over V. So from this relation I have written here, if you understand how I went through the mathematics, let me clean the whole of this and write it boldly so I can see it. So I'm going to get 1 over F is equal to 4L over V plus 4C over V. So if we plot a graph of 1 over F against L, that graph should give us a straight line. This is a straight line graph. When we compare this one with y is equal to mx plus c. Our y is 1 over f, our x is L. So the slope of the graph is going to give us 4 over v, and the intercept of the graph is going to give us 4c over v. The whole intercept is equal to 4c over v. Good. Now you see the reason why when I performed the experiment, I had to find the inverse of the frequency. I had to do that because of this relation that I have here, so that I can plot a graph of 1 over f against L. So when I plot this graph, a graph of 1 over f against L, when I plot a graph of 1 over f against L, graph of 1 over f against L, like this. Graph of 1 over f, that is f inverse stroke hertz inverse. 1 over f stroke hertz inverse, and then L stroke centimeters. Now, if I do this, then the graph will give me something like this. The graph will give me something like this. How did I know that the graph will give me something like this? When you look at this relation, the n, which is the slope, its corresponding value in this relation is 4 over v. That is positive. So the slope of this graph, s, which is going to give me 4 over v, the slope of the graph is positive. So we are supposed to have a positive slope. That is 1. Now the intercept, c of the graph, its corresponding value in the relation is 4c over v. So the intercept is also positive. Because the intercept is positive, to cut the 1 over f axis at a positive point here. If the intercept were negative, I would have extended this one and then the graph would cut this one at negative point. But because the intercept is positive, because the intercept is positive, it is cutting the 1 over f axis at a positive point. So the intercept here, I is equal to 4c over v. Good. So once we have our graph like this, we determine the slope and we use the slope to find the velocity of sound in air. But luckily enough, we are going to kill 2 birds with 1 stone. Why? We are also going to determine the end correction of the pipe. Remember, there are 2 factors that affect the end correction: the radius of the pipe and temperature. Good. Later, I'm going to talk about that under the precautions. So, we find the intercept of the graph. Having found the velocity of sound in air, we put the velocity of sound here, we put the intercept, and then we find the end correction c. So now, we have described an experiment to determine the end correction, and we have described an experiment to determine the velocity of sound in air. Thank you very much. So this is all that has to be done in the determination of velocity of sound in air using resonance tube. Good. So if you have any question for me on this, go to my Facebook page, BJ's Physics Classroom. Post your question there. I will look at it and then I will answer you. If it requires that I'll do a video of it, I'll do a video of it and I'll send it. If it doesn't require that, I have to answer you by text. I will text you with it. Good. Now, in doing every experiment, you need to take care of certain things that we call precautions. So 1, remember that the temperature of the room affects the velocity of the sound. Why? Because the temperature affects the end correction and it also affects the velocity of the sound. So you make sure that the room is ventilated enough so that the atmospheric temperature or the normal room temperature, which is 25-30 degrees Celsius, will be achieved. If the room is too hot, the velocity of sound in air is going to be affected. So 1, that is one precaution you need to take note of. 2, when you sound the tuning fork and you bring it, when you sound the tuning fork and you bring it to the end of the open pipe, make sure it doesn't touch the edge of the open pipe. If it touches the edge of the pipe, it's a closed pipe, sorry. When it touches the edge of the pipe, it will stop vibrating. So that's a precaution. Don't let it touch it. If you touch it, you let it touch it, you disturb it. So make sure that it is placed at a point here, so that at the end of the day, the end correction is going to be taken care of. You understand that? Good. The next precaution number 3. In reading the length, make sure you read the length from the meniscus level of the water. Remember, water has a concave meniscus. So when reading the length of the pipe, you read it from the meniscus level. If you read it from the edge of the pipe, you are going to encounter problems. Another precaution you need to take care of when doing this experiment is that make sure there is not too much noise in the room. When there is too much noise in the room, remember you are going to listen to sound. So when there is too much noise in the room, the noise will disturb the sound and you may not hear the resonance occurring properly. And if you don't hear the sound properly, sometimes the sound comes in and then graduates into the actual resonance. If you don't take care, it will get to a point where you think that resonance has occurred, but resonance has not occurred. It is because of the sound in the room. So make sure the sound in the room is as minimal as possible. Good. So in order to state that precaution, you say that the room is kept under serene condition, or the sound in the room is kept at as minimal as possible, so that you can have a very peaceful practical. Thank you very much for being part of the show today. This is how we describe a simple experiment to determine the velocity of sound in air. And also the end correction, even though that wasn't part of the discussion, but alongside it has come in. I knew it was going to come in. Good. So like I said from the beginning, make sure you put on your nose mask everywhere you go. Please protect yourself. Now that I'm done and I'm going to go home, I'm going to put on my nose mask whilst I'm going home. But subscribe to my YouTube channel, BJ Online, and if you haven't subscribed, please do that. Let us get, when we do that, anytime I post a video on that page, you will receive a notification. Once you do that, also turn on the notification button so that when I post a video, you receive a notification and then you watch it. Good. Thank you very much. It's been a wonderful day.